So a little bit more graphic today, and then we'll start talking about L'Hopital's rule, which I know one of your classes has started covering, but all of your classes should cover at some point. In fact, in this example and in another example, we're going to come back and look at them using L'Hopital's rule after we've talked about it, because there is something important to say. But let's go ahead and find the things. So we're going to graph this eventually. So we're going to find all the usual things like the intercepts, the critical points, the second derivative critical points. I've left off the asymptotes, and that's with good reason. We will talk about them, though, once we start graphing. So let's go ahead and find the intercepts. So my y-intercept, we're going to set x equal to 0, and we're going to get f of 0 equal to e to the 0 plus 0 times e to the 0, which is 1 plus 0, just 1. For x-intercept, I'll say this again. Last time I said it, when you're trying to find the y things, an unfactored form is preferable usually. When you're trying to find the x things, we usually prefer to factor as much as possible. So if I'm trying to find the x-intercepts by setting the whole function equal to 0, instead of writing it as e to the x plus x e to the x equal to 0, I'd rather factor out an e to the x and write it as e to the x times 1 plus x equal to 0. And then we set each factor equal to 0, but we have to keep something in mind here. If we set 1 plus x equal to 0, no problem. We get x equal to -1. If we set e to the x equal to 0, that is a problem. There aren't going to be any solutions there. Something I would encourage you to remember or say is e to the anything is always positive. Think about the graph of e to the x, right? The graph of e to the x is always above the x-axis, so it's always giving you positive value outputs. In fact, any positive number to any power is always positive. So I'll just stay up here. B to the x is positive for any x if b is already positive. Comes up relatively often, actually. All right, so our only x-intercept is x equal to -1. This part here has no solution. We're going to skip the asymptotes, but I will point out this expression here definitely has no vertical asymptotes. So just as an aside here, no vertical asymptotes because there's no logarithms and there's no potential division by 0. That's what we're always looking for. We're looking for vertical asymptotes. And then we'll talk about horizontal asymptotes later. For the critical points, sure. Let's go ahead and use another piece of paper here. So we're going to take our derivative. If I can move this piece of paper around. Maybe. So critical points. So our function, again, is e to the x plus x e to the x. And the derivative is going to be a little bit different, but not a whole lot different. The derivative of e to the x is still e to the x. The derivative of x times e to the x, you have to use the product rule. So it's going to be 1 times e to the x plus x times the derivative of e to the x, which is still e to the x. And we're going to take that derivative and, I mean, it is our derivative, but we're also going to set it equal to 0 to find our critical points. And just like before, when we were finding the x-intercepts, when we want to find critical points, we're still trying to find an x thing. So it's almost always to our benefit to factor as much as we can. Here we can see each term has an e to the x. So we're going to factor that out and be left with a 1 plus a 1 plus an x. And simplifying that just a little bit more, we get e to the x times 2 plus x equal to 0. I'll also point out, it's really good to have the factored form of your derivative, because when you're trying to do the sign chart for your first derivative, it's much, much easier to tell if the thing is positive or negative by plugging in points to your derivative, into your factored derivative, as opposed to this thing here. So again, we know e to the x can never equal 0, so we're not even going to bother saying it. We're just going to say, well, 2 plus x equals 0, so we're going to get x equal to -2. Let's go and figure out what kind of critical point we have. Is it a maximum, is it a minimum, or is it neither? It could be neither. So we're going to use a sign chart. We're going to put our only critical value on the sign chart. It's -2. I don't care about anything else. F prime over here is e to the x times 2 plus x. Here is a really good time to remember that e to the x is always positive. That's going to help us figure out the sign of this whole thing. So if I pick something bigger than -2, like 0, e to the 0 is positive, and 2 plus 0 is positive, and a positive times positive is positive. If I pick something less than -2, like -4, e to the -4 is positive. I don't know what it is, but I know that e to the anything is positive. And 2 plus -4 is negative. So a positive times a negative is going to give me a negative result. So it looks like our function, come on, pens. Our function is decreasing left of our critical point and increasing right of our critical point, meaning we have a relative fill in the blank. At least in your head, if not on paper or whatever writing thing you're writing on. X equals -2 is a relative minimum. Now, I will point out here, this is where things get a little bit weird, because we're going to find the y-coordinate, but it's not going to be very nice. So just to find the y-coordinate is going to be f of -2. Now be careful here. I'm not plugging into the derivative. I'm plugging back into the original function. So that's going to be e to the -2 plus -2 times e to the -2. I have 1 of something minus 2 of something. So that's going to be -1 times e to the -2. Or I might even write it as -1 over e squared. The reason I'm doing this is so I have an idea of about what it's going to be when I graph it. This is a very, very, very tiny number. E squared is approximately 8. So this is approximately -1/8. And again, we don't really need to write that down. We just are hoping to use that when we graph it. All right, we found our first derivative stuff. Let's find our second derivative stuff. So you have options here, and I'm trying to decide which option I prefer. I could either use this version of my first derivative to take the second derivative, or this version, and either one is fine. It doesn't actually really matter. They both kind of end up being the same amount of work. Let's go ahead and use this factored version here. So my first derivative is e to the x times 2 plus x. My second derivative, I'm going to use the product rule. So it's the derivative of e to the x times 2 plus x, plus leave e to the x alone and multiply by the derivative of 2 plus x, which is 1. Again, we factor out the e to the x. By the way, when you have ones like this, you almost are always able to factor out an e to the x or an e to the negative x if it's e to the negative x. So that's equal to 0. We're going to factor in e to the x. Look what we're left with. We get e to the x times 2 plus x plus 1, which ends up being e to the x times 3 plus x, or x plus 3. So we're going to end up getting a second derivative critical point of x equal to -3. Something I think is interesting, but not that important, is if you took the next derivative of this, you know what you would get? You'd get e to the x times x plus 4. If you did it again, it'd be e to the x times x plus 5. It's kind of a neat pattern here that just happens to crop up. So when you have e to the x times x, or e to the x times, or e to the negative x times x, often every derivative just kind of moves it one to the left or one to the right, kind of, which is kind of neat. Let's go ahead and draw our second derivative sign chart. Again, this is going to tell us about the concavity of this function. We're going to put our only critical point on there, which is x equal to -3. And then we're going to look at both sides of this. And again, if we look at our fully factored form, which is e to the x times x plus 3, it's not too terrible to see that if you plug in 0, in fact, if you plug in 0, you can actually calculate it. Right? E to the 0 is 0. 0 plus 3 is 3. And sorry, whoa. I said something that was not true. I was talking too fast. E to the 0 is not 0. E to the 0 is 1 times 0 plus 3 is 1 times 3, which is 3. So if you plug in the 0, which is over here, the whole thing is positive. If you plug in something like -5 over here, -5 plus 3 is negative. E to the anything is positive, and a positive times a negative is negative. So over here, we're concave down. Over here, we're concave up. So we do indeed have an inflection point, which we should abbreviate as IP, at x equal to -3 and y equal to f of -3. Yeah, which if we look back at the original function is going to be e to the -3 minus 3 times e to the -3. Or in other words, -2 times e to the -3. Sorry about that. I don't think it's as important to know what the inflection point y value is. Like, I know I wrote this here. I'm not even thinking about what that is. I'm just like, yeah, it's going to show up when we graph it. And I would really encourage you not to worry too much about the second derivative information when you're trying to draw the graph. It'll usually just kind of, with some weird exceptions, it'll usually just play out how it's supposed to. Meaning, as long as you draw the graph according to kind of the rules we know and the first derivative information, things should work out all right. So let's go ahead and see what we get when we start graphing this. So before I actually draw the graph, I'm going to put all the important information on there that I can. So I know I have an intercept at where? I think it was at -1. Yes, I have an x-intercept at -1. My y-intercept was at +1. My critical point, my first derivative critical point, my relative minimum was at -2 comma -1 over e squared. Okay, so here's where I'm going to be a little bit more dramatic. I don't really want to draw that. Like, -1/8 is, right, it's really not a lot of distance to work with. So I'm just going to draw it about there and make it. And then I'm not even going to worry about my critical point being, for my second derivative being over here at -3. So I've got this point, and this point. And here's something really important. So we know that up until we get to -2, which is right here, we're going to be decreasing, coming down. And then after -2, we're going to be going up. There's something else to be aware of, though. This graph only has one x-intercept. It's right there. That is the only place where we can touch the x-axis at all, let alone cross it. Meaning, over here, since we have to be below the x-axis, we can't cross again. So the way we're going to be decreasing from the left until we get to -2 comma whatever is like this. So let me use a different color here. So we're kind of forced to draw that horizontal asymptote there because we have no other choice. We can't cross the x-axis, but from the left, the graph, like as you move further left, the graph has to be getting closer and closer and closer to the x-axis because it's getting, and this sounds kind of wrong, but it's getting bigger as we move to the left. Or when we come from the left, it is decreasing. So I would probably choose to label these points. This here is -2 comma, I believe I said it was 1 over e squared, -1 over e squared, sorry. And this point here, which is my inflection point, is whatever we just said it was. -3 comma, I think it was -2 e to the -3rd. And it looks like my concavity is probably right. It's certainly concave up here, right? We can see it's opening upwards. And over here, it's less easy to see, but it is opening downwards over here. Another way you could think about this. There's actually two ways to think about it. One way, which I was trying to tell someone the other day, I feel like I wasn't quite doing right, is if you imagine like this is a road and you're looking at the top of a map, and you imagine like a car driving on this road. At this point, even though it's very, very slight, the car is turning slightly to the right. And then right here at the inflection point, the car starts making a left-hand turn like that. Or you could use the tangent line thing. If the function is concave down, any tangent line, even though they're hard to draw here, should be above the function. And if the function's concave up, any tangent line should be below the function. I have a better example of that coming up in a couple graphing examples. So I will point out, we do have a horizontal asymptote, but it's only one-sided. If you look at, as we go to the right, there isn't a horizontal asymptote. So the limit as x approaches infinity of our original function, which was x plus 1 times e to the x, I factored it instead of writing it as x e to the x plus e to the x. But if you let x get really, really big, that's a big thing times a big thing, that's going to be a big thing. So there's no horizontal asymptote to the right. However, to the left, moving the limit as x goes to negative infinity of x plus 1 times e to the x, I might choose to rewrite this as the limit as x goes to negative infinity of x plus 1 divided by e to the negative x. This is not stupid to do, even though I might be like, why are you doing this? This is actually really, really important when we start talking about L'Hopital's rule in like 20 minutes. So what's happening here is the numerator is getting really, really, really negatively big. I've got negative infinity plus 1. The denominator is also getting really, really big. E to the negative infinity is e to the infinity, which is a gigantic number. This is also very big. Now, you might be able to convince yourself, and I think we all can, that one of these infinities is much, much larger than the other. If you were to graph y equals x plus 1 and y equals e to the negative x and compare how fast they got big, we can see that e to the negative x, as you go to the left, shoots up like this, whereas x plus 1 goes at a very linear pace, which is not super fast. So this infinity on the bottom is much, much larger. In fact, let's draw it bigger to make sure we know. It's a bigger infinity, and so this is going to go to 0 because the denominator outpaces the numerator. But later on, we will see using L'Hopital's rule that this limit is also 0, which is good to know. Because that's how you actually find the horizontal asymptote here, is by taking the limit to negative infinity and then use L'Hopital's rule to show it's equal to 0. All right. Let's do, I know I said I had 2 more graphing examples. Let's do one more kind of, because they do get to be a bit tedious, right? There's so many things to take care of. So there's really just one more I want to show you because it's got some really nice points and there's some cool things to see. So we'll try to do this next one without doing too much work. Remember, see if I remember what it is. So we're going to graph something actually kind of similar, although a little bit more complicated. G of x equal to x to the 4th times e to the x. Yeah, let me make sure that's the right one. And it is the right one. So if we know we're going to graph a thing, we know we have to find all the things. I would probably start off by, well, the same way I've done it every time. I know you said we're not going to do all the things, we're probably going to do all the things because it's hard not to show all the things. So let's start off with the intercepts, but we'll do them fast. So the y-intercept, x equals 0. G of 0 is 0 to the 4th times, I shouldn't really even think about the next part, because 0 times anything is 0. Well, there's an exception to that rule, but we'll talk about it later. And then the x-intercept, here's something good to know. If you know that y equals 0 is your y-intercept, you know that x equals 0 has to be at least one of the x-intercepts. So if we set the whole thing equal to 0, well, we can set each factor equal to 0, but we know that setting e to the x equal to 0 won't yield any results. There's no solution there. So we only get x equal to 0. So our only intercept is the origin, 0, 0. Let's find the... So let's talk about the asymptotes for a second. Oh, question, sorry. Yeah, well, it is 1, but I have 0 times 1, which is 0. Yeah. Yeah, I wasn't making that mistake yet, although it was close. Let's talk about asymptotes for a minute. So vertical asymptote, there isn't any. Horizontal asymptote, there is going to be one. Similar to the previous problem. If we take the limit as x goes to positive infinity of x to the 4th times e to the x, nothing special happens. We don't get a number. We get a really big number times a really big number, which is going to be a really big number. But if we look at the limit as x goes to negative infinity of x to the 4th times e to the x, now we have a really big number, actually infinity times e to the negative infinity is really, 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 really small, right? If you think about the left side of the graph of e to the x, we're getting closer and closer and closer to 0. So this is actually what's called an indeterminate form. It's another indeterminate form. It's infinity times 0. And just like 0 divided by 0, like we saw way back with the limit definition, or infinity divided by infinity, this can end up being anything. In this example, it is going to end up being 0. But I want to stress 0 times infinity is not always 0. Because really, we're not saying we have 0 times infinity. We're saying we have a really big number times a really small number. And those can kind of balance out sometimes and be kind of anything. But in this case, we do get the limit as x goes to negative infinity of x to the 4th divided by e to the negative x. And then just like e to the anything, e to the negative x outpaced x before, or x plus 1, e to the negative x is going to outpace any polynomial function. So you could have x to the 4th or x to the 400th here, and this denominator would still eventually beat it out and get larger and larger and larger faster. So this is going to end up being a smaller infinity over a bigger infinity, which is going to go to 0. And again, I promise you, as soon as we talk about L'Hopital's rule, we'll come back and see that, oh yeah, this really is going to be 0. Let's look at the first derivative stuff. Our first derivative is, well, it's going to require the use of the product rule. It's going to be 4x cubed times e to the x plus x to the 4th times e to the x. We're going to set that equal to 0. And unlike last time, we can factor out more than just e to the x. We can factor out an x cubed times e to the x from both parts. So we're going to have x cubed times e to the x factored out, and we're left with a 4 plus an x. So in this case, we're actually going to get 2 critical points for the first derivative. We're going to get x equal to 0 by setting x cubed equal to 0, and we're going to get x equal to negative 4 by setting 4 plus x equal to 0. And we're not going to get anything by setting e to the x equal to 0 for the same reasons we said that last time. So then on our number line, we have 0. Ah, damn. Oh well, I'll live. And negative 4. Yeah, I'm disappointed in myself. I meant to do e to the negative x. Oh well, such is life. I had a really cool picture to show you, but I think I can fix it properly. All right, so picking a number larger than 0 like 1, positive, positive, positive. Picking a number between 0 and negative 4 like negative 2, negative, positive, positive. Picking something like negative 5, negative, positive, negative. So overall positive. So my function is increasing, then decreasing, then increasing. We could write down the intervals for increasing or decreasing. That's not something that's usually required, but if we wanted to, we could say it's increasing on the interval from negative infinity to negative 4, union 0 to infinity, and it's decreasing on the interval from negative 4 to 0. We have a relative minimum and a relative maximum. The relative minimum is at 0 or -4? 0. 0 comma the y coordinate we already have is also 0. We have a relative maximum at -4 comma whatever f of -4 happens to be. For ones like this, I don't usually try to worry about the y values too much. Let's look at the second derivative stuff. Yeah, is that all we need there? I think that's all we need. So, second derivative. Now, at this point, I would probably use this version of the first derivative to take the next derivative as opposed to this version, although really you'd be fine either way. But I'm going to do it this way. So for each of these pieces, let me just write g prime here. For the 4x cubed times e to the x and the x to the fourth times e to the x, we're going to have to use the product rule for each of those. So for this first part, the derivative of 4x cubed is 12x squared times e to the x, plus you switch it, leave the 4x cubed alone, multiply by the derivative of e to the x, which is e to the x. Plus, now we do it for over here. Now I'll point out, we already know what the derivative of that is. That's the first thing we did in this problem. We took the first derivative. The derivative of x to the fourth e to the x was exactly 4x cubed e to the x plus x to the fourth e to the x. So we should just write that down again. We should save ourselves the mental work of finding that derivative again, since we have already found it. And then we're going to factor, well, we're going to simplify and factor. So 4x cubed plus 4x cubed gives me an 8x cubed. So I have a 12x squared times e to the x plus an 8x cubed times e to the x plus an x to the fourth times e to the x. And from each of these terms, I can factor out an x squared and an e to the x. And I'm left with 12 plus 8x plus x squared. And I feel like I've really written this in the backwards order, right? Because if I wanted to try and factor that, it's much more typical to write it as x squared plus 8x plus 12. But if we have x squared plus 8x plus 12, I can definitely think of two numbers that multiply to 12 and add up to 8. They're 2 and 6. So this factors as x plus 2 times x plus 6. So we end up getting x squared times e to the x times x plus 2 times x plus 6 equal to 0. And so we end up getting 3 critical points here. We get x equal to 0, we get x equal to -2, and we get x equal to -6. This problem, in my opinion, is a great test question because all the numbers come out relatively nice for your first and second derivative. You get nice x values. Your y value is okay, not so nice, but relatively speaking, it's not too bad. Putting these all on the number line in the correct order, and then seeing what's going on with our second derivative here. Again, I'm looking at the fully factored form to do this. So here's what I should really say about this. You should ignore the e to the x. E to the x is always positive. It's never going to change the sign of your expression. So really, I should just be looking at the x squared, the x plus 2, and the x plus 6. If I pick something bigger than 0, like 1, positive, 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 positive. And then, instead of continuing to check points, we can do the other thing where we look at the powers of the factor that the 0 came from. So this 0 came, or critical point, came from x to the second. Having an even power there means the sign is going to stay the same. This -2 came from x plus 2 to the first. The odd power there means the sign is going to change. Similarly, the -6 came from the x plus 6 to the first. The sign is going to change because of the odd power. Or you can check points. If you plug in -1, that's going to be positive, 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 positive. Plug in -3, positive, positive, negative, positive. You plug in -7, positive, positive, negative, negative. So either way you want to do it's fine. Just the other way I did it was a little faster. All right. So what does that mean for us? It means it's concave up over here, it's concave down over here, it's concave up over here, and it's concave up over here. Interesting. So that means we have an inflection points at -6 and -2. So at -6 comma f of -6 and -2 comma f of -2. So how do we draw this thing? Well, we plot the things we have. So something I think will make this a little bit easier to see what's going on is the following. Yes. Sorry, there's so many pieces of paper to keep track of here. So we know all of our important points are negative, so we should give ourselves more room on the left side of the graph. Right? Something good to do if you have the option to draw your own axis. I'm going to draw it like this, so that most of the stuff is happening over here on the left. I don't really care what's happening on the right so much. So let's go back and look and see what we have. We have our y-intercept of 0 and our x-intercept of 0. And then we have things happening at -2, and -4, and -6. All right. Something else I would probably could have said to myself before I started graphing this was x to the fourth times e to the x is always going to be greater than or equal to 0. X to an even power is always non-negative. E to the x is always positive. And so those are going to multiply something positive. So I know my graph is always going to be above or touching the x-axis. All right, so we have, what else do we have here? We had a relative minimum at 0, 0. And we have a relative maximum at -4, comma, whatever f of -4 was. All right, so f of -4. Well, that's going to be kind of gross. It's -4 to the fourth times e to the -4. I'm not trying to actually find the value here. I'm trying to get an idea of what's going on. 4, or I should say -4 to the fourth is going to be +4 to the fourth divided by e to the +4th. That's 4 over e to the fourth, which actually isn't that bad because 4 over e, it's like 1 point something. When you raise that to the fourth power, it gets a little bit bigger, but it's going to be, you can convince yourself this is not too big. Or you know what you could do? You could use a calculator, right? It's not a crime to use a calculator. Let's see what we've got. Let's see what we've got. So if we do 4 divided by e, where'd you go, e? The problem with not using this calculator very often. Where is e? Good question. Let's just do this. 4 to the fourth divided by e to the fourth. About 4.6, 4.7. So not like out of this world, right? It's very graphable. So right about there, my 4 comma f of, sorry, my -4 comma f of -4, that's about where my relative maximum is. And so we're going to draw this. We know we have a horizontal asymptote out to the left. It's going to look something like this. Come up. It's going to top out. Turn around. It's going to kind of maximize the first derivative right there. That's about as steep as the first derivative is negatively. And then it's going to start becoming less steep. That's where your inflection point is. Bottom out there, and then increase afterwards. So if I look back at my first derivative sign chart, that seems to be okay, right? It's increasing until we get to -4, decreasing from -4 to 0, and increasing from 0 onwards. And then my concavity looks about right. At -6, you could probably convince yourself you have an inflection point there, right? It's my tangent lines are below over here and above over here. Similarly, the one at -2 I did not draw as well, but you could probably convince yourself tangent lines over here are above and tangent lines over here are somewhere below. So that's that function, and that's kind of as much as we need. Now, what I wanted to show you, but I blew it because I accidentally did the slightly wrong function. But there's just one thing I want to show you, which I think is kind of neat. So let's see if I can I fix it fast? I might be able to fix it really fast. So here's the function I actually meant to show you, which was x to the fourth times e to the -x. Yeah, I don't think that fixes so easily, unfortunately. Yeah. So anyway, let me just point out, because there's something I want to show you. This function has essentially all the same pieces, except it's flipped. Everything is on the right side instead of the left side. So my relative maximum is at 4 comma f of 4. And my relative minimum is still at 0 comma 0. And my inflection points are at 2 instead of -2 and 6 instead of -6. But here's the point I really actually wanted to show you. We can also draw the tangent line anywhere. So that black line on the bottom there, that's actually the tangent line at 0. But if we move it over just a little bit, you can see that before I get to that inflection point, the tangent line is underneath the graph. And then when I get right to that inflection point, the tangent line actually goes through the graph. On the left side, it's below. On the right side, it's above. We can even zoom in to really, really see it. Whoa, too much there. Right? You can really see, oh yeah, on the left side, that tangent line is below the red graph. On the right side, it's above. And then, that's a little bit too much there. As you keep moving to the right, the tangent line is now above the graph because it's concave down, still concave down, still concave down, flattens out at the maximum, right? Oh, geez, can I do that there? Maybe. Sorry, not a very straight hand, right? Tangent line has a horizontal, derivative is 0. Keep moving, tangent line's above, and then when we get to this next inflection point, it's as steep, it's as negatively steep as possible. And then after we move to the other side of it, if I can stay there for just a second, then we become the tangent line underneath the graph. So when it's concave up, the tangent line is below. When it's concave down, the tangent line is above. I think that's a really helpful way of thinking about how we actually need to look at these things, because it's hard. It's really hard, in my opinion, to look like way over here when you're graphing it by hand and be like, yeah, it totally looks concave up over there. No, it doesn't. It looks like it's practically flat. So you have to be able to say, well, okay, if I drew a tangent line, would it be under the graph? All right, then it looks like it's concave up. Or again, if you want to use the car idea, you could say, well, that car is turning slightly to the left if you're looking at it from the top down view. But those are some ways to think about how to draw things so the concavity looks correct. I also think it wouldn't be a bad idea if you're interested. I will post this graph to Canvas, but I'll also just tell you, you all should try on your own to graph that one, which is f of x equal to x to the 4th times e to the -x. And see if you can find all the same critical points and then compare it to what's over there. It's worth looking at when you have time, if you have time. I know you all have limited amounts of time because you're students and you have lots of other classes, not just this one. All right. Reminder to myself to actually post that. All right, I think that's enough graph. Let's go ahead and talk about L'Hopital's rule, which you might have heard of before. Yeah. Okay. Do me a favor and say L'Hopital. Don't say La Hospital. It's L'Hopital. I mean, it's okay to say it wrong if you really want to, but it is a name. We try to pronounce it correctly. So L'Hopital's rule. I'm just like, oh yeah. So how do I want to say this? Yeah. So here's the gist. L'Hopital's rule is a rule that allows us to find limits. I'm going to say this again. We only use L'Hopital's rule to find limits, nothing else. You have to be taking a limit of something to be able to apply L'Hopital's rule. So if you're trying to find some derivative somewhere, L'Hopital's rule is not in the game. But if someone asks you to say, like, find the limit as x approaches infinity of, I don't know, x to the 4th over e to the x, well, then we've got a problem because the top is getting infinitely large and the bottom is getting infinitely large. What do we do? Well, we should probably say what L'Hopital's rule is. So here's the rule itself. There's two situations in which you're allowed to use L'Hopital's rule. If you have the limit as x approaches a of f of x over g of x equal to either 0 over 0 or the limit as x approaches a of f of x over g of x is any sort of infinity over any sort of infinity. What I'm saying there is it doesn't have to be positive infinity over positive infinity. It could be a positive infinity over a negative infinity, or a negative over a positive, or a negative over a negative, or right? Any combination of positive over negative, or negative over positive. If either of these two cases are the case, these are the only cases where you can use L'Hopital's rule. Anything else, you have to do some work first. Then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of the derivative of f of x over the derivative of g of x. That's it. That's the whole deal. So we'll come back to this example in a minute, but let's look at some examples we actually know the answers to already. For example, the limit as x approaches 3 of x squared minus 9 over x minus 3. If you plug in 3, what do you get? Finish the statement. 0 over, right, which is a very different thing. 0 is a number. Great, we love it. It's the best. 0 over 0 is a I don't know. We have to do something. And before, way back when we were just doing limits before the L'Hopital's rule, we could have done this one by just factoring and canceling. We could have said, oh yeah, that's the limit as x approaches 3 of the top is x minus 3 times x plus 3. The bottom is x minus 3. The x minus 3's cancel, and we can say, great, the limit as x approaches 3 of x plus 3 is just 3 plus 3, which is 6. And it's totally fine to do it that way. It's allowed, you still can. But we also could have, or could now, say the limit as x approaches 3 of x squared minus 9 over x minus 3. Well, since it's a 0 over 0 type, we can say, great, we're going to use L'Hopital's rule. When I use L'Hopital's rule, I like to write an L apostrophe H above the equal sign so that the person reading my work knows I'm using L'Hopital's rule in that spot. We still have to write the limit as x approaches 3. And now we're going to take the derivative of the top divided by the derivative of the bottom. And now it's no longer an indeterminate form. It's not 0 over 0 anymore. We can just plug in 3 for x and get 2 times 3 divided by 1, which is 6, which is the same answer, which it should be, right? It shouldn't matter which way you do the limit. You should get the same result either way, as long as you're doing the right work. So why talk about L'Hopital's rule if you could just do it this other way? Well, not every limit can be done another way. This limit up here, we can't do it that way. Let me give you one more example of an indeterminate form that we could have done a different way before we do some of these ones where we can't. So here's something that should also look vaguely familiar to you. The limit as x approaches infinity of 3x squared plus 4x plus 2 over 7x squared minus 5x minus 8. And I think you all remember that if I take this limit where the degree on top and the degree on the bottom are the same, the answer should be what fraction? Yeah, it's going to be 3 over 7. You could show the work, right? The work is dividing everything by x squared and getting 3 plus 4 over x plus 2 over x squared over 7 minus 5 over x minus 8 over x squared. And then saying, oh yeah, the 4 over x and the 2 over x squared and the 5 over x and the 8 over x squared all get really, really small. And so we're left with 3 over 7. Or we could use L'Hopital's rule. This is an infinity over infinity. So we can say that this limit as x approaches infinity of 3x squared plus 4x plus 2 over 7x squared minus 5x minus 8. We can apply L'Hopital's rule. We still have a limit as x approaches infinity. You always have to still have a limit if you're using L'Hopital's rule. It's saying a limit of a thing is equal to a limit of a different thing. It's the limit of the derivative of the top, which is 6x plus 4, over the derivative of the bottom, which is 14x minus 5. And if we plug in infinity now, we get 6 times infinity plus 4 over 14 times infinity minus 5, which is still infinity over infinity. So we do it again. We use L'Hopital's rule again. And now we get the limit as x approaches infinity of the derivative of 6x plus 4 is 6. The derivative of 14x minus 5 is 14. And the limit of any constant is just that constant. So we get 6 over 14, which reduces to, surprise, surprise, 3 over 7. So the point of these two examples was just to show you that L'Hopital's rule really does work, right? Whether you already have another method of doing that limit or not, L'Hopital's rule will get you to the right answer as long as you're applying it correctly. And by applying it correctly, I mean only using it when your fraction or quotient is either a 0 over 0 or infinity over infinity. Those are the only times you can use it, never, ever, ever any other time. So let's actually go back and look at that first example of the function we graphed. When we graphed f of x equal to x plus 1 times e to the x, or if you prefer, x e to the x plus e to the x, we said there was a limit as you went to the left. We said there was a horizontal asymptote. I claimed that the limit as x goes to negative infinity of this expression was equal to 0. Well, now we're going to show it. So I will say, when you're using L'Hopital's rule, it usually is better to write it in a factored form versus an unfactored form because it makes it easier to turn it into a fraction. So if I have the x plus 1 times e to the x, notably, this is not in the right form. It's not a fraction. It's not a 0 over 0 or infinity over infinity. So before I can even think about using L'Hopital's rule, I have to rewrite it in a way so that I can use L'Hopital's rule. I have to write it as a fraction. Typically, that means bringing one of the two terms to the denominator as its reciprocal. There's almost always a better choice. The wrong choice here, and yes, I will say the wrong choice, is to write it as e to the x over 1 over x plus 1. That is not going to help us out. It's just going to get worse and worse and worse. On the other hand, the right choice is to write it as the limit as x goes to negative infinity of x plus 1 over 1 over e to the x. Except that's not really the right choice. The right choice is to rewrite 1 over e to the x as e to the negative x. So what we're really going to do here is we're going to rewrite this as the limit as x approaches negative infinity of x plus 1 divided by e to the negative x. And at least from my point of view, it is the easiest in this form to see that we have something that is going to negative infinity on the top and positive infinity on the bottom, which is one of the okay indeterminate forms to use L'Hopital's rule on. We have some sort of infinity over some sort of infinity. They do not have to match. So then we can say, great, L'Hopital's rule is going to get us to the limit as x approaches negative infinity of the derivative of x plus 1, which is 1, over the derivative of e to the negative x, which is e to the negative x times negative 1. And now if we plug in negative infinity, we get 1 over something really, really, really negatively big, right? That's e to the infinity times negative 1. So if you want to, you can write 1 over negative infinity. I like to put little quotations around that because it's not really something we write. We're really going to say we get a limit of 0. Because 1 divided by a very large number, whether it's positive or negative, is getting closer and closer and closer to 0. In fact, I shouldn't have said 1 there. I should have said any constant, right? That could have been a billion divided by something that's getting infinitely large, still is going to have a limit that's 0. Doesn't matter how big your constant is, infinity is always going to overrun it, whether it's negative or positive infinity. Okay. Well, before I forget, let me pass out the attendance form. So, oh, and that also goes for the other function we graphed, the f of x equal to x to the 4th times e to the x. If you look at the limit as x approaches negative infinity, this one's a little bit dicier. Again, I've got the same sort of problem. I will point out, because this is something people see a lot, this original form is what's called an infinity times 0. This is one of the indeterminate forms we should recognize, and we can't use L'Hopital's rule yet, but any indeterminate form like this, where it's an infinity times 0, you can always rewrite in a way so you can do it. And I would say you usually want to bring the thing to the bottom that's easier to take the derivative of. And easy is not a great word to use there. Yeah, it's like there's no better way to say it though. Usually you bring e to the x to the bottom if you can. Or if you don't have an e to the x, bring a power of x to the bottom. Trig functions usually not, logarithms especially not. So I want to rewrite this as the limit as x approaches negative infinity of x to the fourth divided by, instead of 1 over e to the x, we really want to write e to the negative x. And then we can convince ourselves, oh yeah, that for sure is an infinity over infinity type. The bottom is going to negative infinity to the fourth power. Sorry, the top is negative infinity to the fourth, which is positive infinity. The bottom is e to the negative infinity, or e to the infinity, which is infinity. So we've got big things over big things. So then we take the limit as x goes to negative infinity. Sorry, I put an L apostrophe H. I'm using L'Hopital's rule there. We take the derivative of the top, the derivative of the bottom. And you can probably see we're going to have to do this a couple more times, because now the numerator is going to negative infinity and the denominator is going to negative infinity. So we have to do it again. We basically have to do this until we run out of x's on top, because the denominator is always either going to be e to the negative x or negative e to the negative x. Whereas the numerator, the power of x, will decrease by 1 every step. So this is going to equal the limit as x goes to negative infinity. Again, I'm using L'Hopital's rule. I'm going to get 12x squared over positive e to the negative x, or negative e to the negative x times negative 1. And then, why don't you guys finish? Do a couple more. So here's how this looks. If we use L'Hopital's rule again, we get the limit as x goes to negative infinity of the derivative of 12x squared, which is 24x, over the derivative of e to the negative x, which is negative e to the negative x, or e to the negative x times negative 1. And finally, our last application of L'Hopital's rule, we get the limit as x goes to negative infinity of the derivative of 24x, which is 24, over the derivative of negative e to the negative x, which is negative e to the negative x times negative 1, or just negative x. And at this juncture, we no longer have an indeterminate form. The numerator isn't infinity or negative infinity. It's just 24. The denominator, though, is getting infinitely large. And a constant divided by a really, really big thing is going to get closer and closer to 0. So you can see, I know it's been a minute since we did that graph, but it really, really was the case that as x went way to the left, or negative infinity, the function got closer and closer and closer and closer to 0. So that is typically how you're kind of expected to find horizontal asymptotes for functions that are more complicated, like usually like x times e to the x or x squared times e to the x. Those functions, often you have to use L'Hopital's rule to find one of the, and there's only one-sided horizontal asymptotes. All right, let's see, what time is it? Okay, we got some time to go. Sure, yeah. So let's look at some more interesting examples. In fact, why don't you all try this one? The limit as x approaches 0 of sine of x over x. I will point out that if you plug in 0, this is a 0 over 0 type. So you should all use L'Hopital's rule to get to the next step. All right, what goes on top? Say it loud. Yeah, cosine, the derivative of sine. What goes on the bottom? Right, the derivative of x. And now, so what I should be saying every time is, every time we use L'Hopital's rule, the next step really should be to plug in whatever x is approaching. And then if you get something concrete, you're done. But if you get something that's still 0 over 0 or infinity over infinity, you have to keep applying L'Hopital's rule. Here, we can plug in, well, we obviously are done using L'Hopital's rule because the denominator isn't 0 or infinity. So we can write this as, if I just plug in 0, cosine of 0 divided by 1. And what's cosine of 0? It's 1. This shows us a thing we saw before. We briefly talked about how this limit was equal to 1 way back when we were talking about limits. So now we have another way of seeing that, oh yeah, this limit is what we thought it was. It's kind of nice. Oh yeah, there's that. Cool, let's do that. So let's look at this next one. Where'd you go? Sorry, I had something in my mind. Where was it? There you are, yeah. Let's look at the limit as x approaches 0 of, yeah, this one's annoying, but worthwhile. X minus tangent of x over x minus sine of x. So again, if you plug in 0, you get 0 minus 0 over 0 minus 0, which is 0 over 0, which is indeterminate. It's the right type of indeterminate, where we can use L'Hopital's rule straight away. So using L'Hopital's rule, it's going to be the limit as x approaches 0, the derivative of the top over the derivative of the bottom. So the derivative of the bottom is 1 minus cosine of x. The derivative of the top is 1 minus, the derivative of tangent is secant squared of x. I've got some bad news. Still 0 over 0. If you plug in 0, cosine of 0 is 1, and 1 minus 1 is 0. And if cosine of 0 is 1, secant of 0 is 1 over 1, which is also 1. So secant squared of 0 is also 1, and 1 minus 1 is still 0. So this is still a 0 over 0. So we use L'Hopital's rule again. Okay, here's where we're going to have to be extra careful. I want to make sure that I'm thinking of secant squared of x as secant of x quantity squared. So that when I take its derivative, I use the chain rule appropriately. So applying L'Hopital's rule, limit as x approaches 0 of, let's see, derivative of 1 is 0, minus the derivative of some stuff squared is 2 times my stuff times the derivative of my stuff, which is the derivative of secant of x is secant of x times tangent of x. The bottom is much less worse. The derivative of 1 minus cosine is 0 minus negative sine, or positive sine of x. Now, here's the bummer. If you plug in 0, you still get 0 over 0. Because secant of 0 is 1, secant of 0 is 1, but tangent of 0 is 0, and sine of 0 is 0. I really don't want to use L'Hopital's rule again, because taking the derivative of the top would be kind of terrible. And I don't have to if I use my trig knowledge appropriately. I'm going to rewrite this in terms of sine and cosine. So what I really have here is the limit as x approaches 0 of, I'm going to write this as -2 times Secant is 1 over which? 1 over its cosine. And then another 1 over cosine. And then tangent is sine over cosine. And then dividing by something is the same as multiplying by its reciprocal. So dividing the whole thing by sine is like multiplying the whole thing by 1 over sine. And look at that. I can cancel out the part that's a problem. I can cancel out the sine of x divided by sine of x is just going to be 1. So then this is great. I just have the limit as x approaches 0 of -2 times, I'm going to write this as 1 over cosine is cosine cubed of x, but then I plug in 0 and I get -2 times 1 over cosine of 0 cubed, which is just 1 cubed. So my answer is -2. So in this problem, my 0 over 0, my indeterminate form that's 0 divided by 0, ended up equaling -2. How strange. A reminder, it's called an indeterminate form because it can end up being literally any value. Okay, let's see. We should do this. Yeah, we should. Okay, there's one more trick I want to show you because, yeah, because. So here's one more. The limit as x approaches 0 of sine cubed of 2x over 5x cubed. And what I really want to tell you is, even though you could use L'Hopital's rule here, it's a 0 over 0 form, you'll regret it. Maybe not in the first step. If I use it in the first step, the limit as x goes to 0. The derivative of 5x cubed is 15x squared. The derivative of some stuff cubed, so it's really the sine of 2x quantity cubed. The derivative of that's going to be 3 times my stuff squared times the derivative of the inside stuff is going to be cosine of 2x times 2. And while that wasn't too terrible, the next step is. This is still a 0 over 0. And if I take the derivative of the top, ugh, it's really, really ugly. And even worse, you're not done then. You still have to apply L'Hopital's rule one more time after that. So from here, you still have to apply L'Hopital's rule 2 more times. Sometimes L'Hopital's rule is not the right tool, even though it's applicable. A better tool here is the one we learned before, where we said, and at least the one I hope we learned before. I'm like, did we learn that? I think we did. Where we want sine of something over the same something. Because we know that sine of some stuff over stuff, if that stuff is approaching 0, sine over 0 over 0 is going to be approaching 1. I believe we talked about that. I think you guys are like, maybe not. Let me ask if this rings a bell. I'm going to rewrite this as sine of x times sine of x. Sorry, sine of 2x, apologies. Times sine of 2x times dividing by 5x cubed. Does that look at all familiar? It's okay if the answer is no. I could be totally misremembering what I've taught this class. It looks like the answer is no. I feel like everyone's like, no, it doesn't look familiar at all. It's okay. So I will tell you anyway, another way of approaching a problem like this. So we know from before that the limit as x approaches 0 of sine of x over x is 1. And more generally, the limit as some stuff approaches 0 of sine of some stuff over, it has to be the exact same stuff. That limit is also 1. So if we can write each of our sines as being divided by the exact same argument that we're taking the sine of, the limit of that part will be 1. So what do I wish I had beneath the sine of 2x here? A 2x. But if I divide by 2x, I also have to multiply by 2x. And I wish I had one here as well. And I wish I had one here as well. But then the x times x times x divided by x cubed, that cancels out. So this ends up becoming the limit as x approaches 0 of sine of 2x over 2x times sine of 2x over 2x times sine of 2x over 2x times 2 times 2 times 2 over 5. And each of these, those each have a limit that is 1. So we end up with an answer of 8/5. It's a much better way of approaching this specific type of 0 over 0 problem. I don't know if you'll see this, but if you do, that's a way you can approach it. All right, let's continue on looking at that. Sorry, notes over this. Yep. So let's look at the following one. The limit as x approaches 0 from the right, from the right, of x times natural log of x. Here's one that throws people off quite often. So if I plug in 0 for x, I get 0 times the natural log of 0. So it's important to remember what's happening to the natural log function as x approaches 0 from the right. And really the best way to remember that is by graphing or knowing what the graph looks like. So if you recall, the graph of the natural log of x looks like this. It's got an intercept at 1, 0, and it's got a vertical asymptote at x equal to 0. So we can see that as the x values approach 0 from the right, the y values go down, 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 getting more and more negative towards negative infinity. So this is a 0 times negative infinity type. Again, this is an indeterminate form. But it's not an indeterminate form where we can use L'Hopital's rule right away. We have to manipulate this so we have a fraction that's the right kind of thing. So, of the two pieces to bring to the bottom, we want to bring the x, because you never bring natural log of x to the bottom. It is terrible, so don't do this. Don't even write this down. I feel like I shouldn't even write this down, but I'm going to. Don't do the limit as x approaches 0 from the right of x over the reciprocal of the natural log of x. Because although the derivative of x is fine, the derivative of 1 over the natural log of x is terrible. So not this. Instead, bring the x to the bottom as its reciprocal. So we're going to rewrite this as the limit, as x approaches 0 from the right, of natural log of x divided by 1 over x. I usually like to write it as the reciprocal, but it's perfectly fine to also write it as the limit as x approaches 0 from the right of the natural log of x divided by x to the negative first. It might even make more sense to write it this way. It's just not what I've always done in my life. So then, oh wait, before I use L'Hopital's rule, I should check that I can actually use L'Hopital's rule. So that's actually why I prefer this version of writing it, because it's easier to see. So we know that as x goes to 0 from the right, the natural log of x is going towards negative infinity. And if x goes to 0 from the right, 1 divided by x, well, if x is getting really, 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 really small, 1 over x is getting really, really big. So I have a negative infinity over a positive infinity. So yes, I'm allowed to use L'Hopital's rule here. So now I'm going to use it. I still have a limit as x approaches 0 from the right. The derivative of the top is 1 over x. The derivative of the bottom is negative 1 times x to the negative second. And here's where things can go the wrong way. If you rewrite this, and I would rewrite this in the way I prefer to write it, and here's what I should really say. I think it's better to write x to the negative 1 if you're going to take the derivative. I think it's better to write 1 over x, or whatever fraction you have, if you're trying to plug in 0 and see what it's actually going towards. And if I write it that way as 1 over x over negative 1 over x squared, I might accidentally trick myself into thinking I should use L'Hopital's rule again. And you could use L'Hopital's rule again here. the bottom is going to, sorry, the top is going to positive infinity, the bottom is going to negative infinity. It's certainly an infinity over infinity type. But if you have the option to simplify an expression before going to the next step, it is often always the right call. Often always. It is often the right call. Not always, but almost always. So what I should really do first is rewrite this as the limit as x approaches 0 from the right of 1 over x multiplied by the reciprocal of negative 1 over x squared. So x squared over negative 1. And then x squared divided by x is just an x. So this is the limit as x approaches 0 of x divided by negative 1, or just negative x. And then you can just plug in 0 for x and get 0. Or negative 0, which is 0. So there's like 4 other types of indeterminate forms. We've talked about 3 of them so far. So here are the indeterminate form types we've talked about so far. So indeterminate forms. Here are the good ones. 0 over 0 and plus or minus infinity over plus or minus infinity. Doesn't matter which plus or minus. Why are these the good ones? Because we can use L'Hopital's rule right away. But then we have the other ones, the less good ones, where we have to first manipulate them. So the other ones that we've seen so far are 0 times some sort of infinity. And here are the other ones we're going to see. Here are the ones we're going to maybe see. Infinity minus infinity. 0 to the 0th power. 1 to the infinitieth power. And infinity to the, is infinity to the 0? Yeah, it's infinity to the 0th power. So I want to make a point here. 1 to the infinity power does not mean 1 times 1 times 1 infinite number of times. What an expression like this means is a number close to 1 raised to a power that's getting bigger and bigger and bigger. An example of an expression like that is the limit as x approaches infinity of 1 plus 1 over x raised to the x power. Right? The inside here isn't actually 1. It's getting closer and closer and closer to 1 as x is larger and larger and larger. Similarly, this exponent isn't actually infinity, it's just getting bigger and bigger and bigger. The thing I really want to point out is this limit is almost never equal to 1. Because you have a number that's just a tiny bit bigger than 1, multiplied by itself many, 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 many times. And it's eventually going to overcome being tiny and get kind of somewhat large. So let's actually do that example. So how do we deal with an example like this? The limit as x goes to infinity of 1 plus 1 over x to the x power. So whenever you have one of these 3 indeterminate forms, one of the exponential indeterminate forms where you have something to a power, we have to use a logarithm. And you have a choice of how to do it. You can either just take the logarithm of your expression like this and say, well, we're going to look at the following. We're going to look at the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x. But the problem is that's not the same thing. And so what this limit is actually going to equal is going to equal the limit as x goes to infinity of e to the natural log of 1 plus 1 over x to the x. And then whatever this ends up being equal to down here is going to become exactly what we have right here. So this is going to end up equaling e to whatever that limit is down there. because you took a natural log, and then we're going to undo the natural log by doing e to that thing. Why did we take the natural log? There's a reason. The reason is so that we can deal with this exponent, right? We want to bring that out of the power. So we're going to rewrite this as the limit as x goes to infinity of x times the natural log of 1 plus 1 over x. So now, instead of having a 1 to the infinity type, we have a, let's see, x is going to infinity. So we have an infinity times, well, if x is going to infinity, 1 over infinity goes to 0. 1 plus 0 is 1, and the natural log of 1 is 0. So we have an infinity times 0 type, which we still have to manipulate, right? It's still not one of the good ones. It's not 0 over 0 or infinity over infinity. So we do one more thing. We bring which part down? Not the natural log. We bring the x down to the bottom as a reciprocal. So we're going to rewrite this as the limit as x goes to infinity of natural log of 1 plus 1 over x divided by 1 over x. Or if you prefer, x to the negative 1. And now this is a 0 over 0 type. The top we know is going to 0 already because it's the natural log of 1. And the bottom, which is 1 over x, well, if x is going to infinity, that's going to be a 1 over infinity, which is going to 0. So this here is the type we're looking for, a 0 over 0. And now finally we're allowed to utilize L'Hopital's rule. Say, all right, it's going to be the limit as x goes to infinity of the derivative of the top over the derivative of the bottom. Something I want to point out. X to the negative 1 is the same thing as 1 over x. So when I differentiate the bottom, I'm going to get negative x to the negative second. And when I differentiate the top, the derivative of the natural log of some stuff is 1 over the stuff. Sorry, that's 1 plus 1 over x. Sorry, it looks kind of gross. Times the derivative of that stuff. And the derivative of 1 plus 1 over x is 0 plus, well, we know the derivative of 1 over x, or x to the negative 1, is negative x times, sorry, is negative x to the negative second. But those essentially get to cancel out now, right? What I really have here, just to make it a little bit more clear, I have the limit as x goes to infinity of 1 over 1 plus 1 over x times negative x to the negative second, or negative 1 over x squared, divided by negative 1 over x squared. And those exactly are the same thing, and when we divide them, you just get 1. And now we let x go to the infinity for the rest of it, and we get 1 over 1 plus 1 over infinity is 0. So we get 1. And we don't say that's our final answer because we remember that it's really e to that number. So our actual answer is e to the 1, which is just e. So I don't necessarily love doing it this way because it's really easy after you've done all this work to forget you have to go jam that back in up there and say it's e to the whatever you got. But it is kind of the easier way to write it all out. So I would probably do it this way. Just make sure you remind yourself, oh yeah, I have to say it's e to whatever answer I actually got. I will mention here that this is actually how the number e is defined. E is defined to be equal to the limit as x goes to infinity of 1 plus 1 over x to the x power. Kind of neat. And then I guess and then I shouldn't do another example because it's already almost 1:30. So I will stop there. We'll talk more about L'Hopital's rule next week, as well as the last topic, which is optimization, which is essentially very similar. It's kind of a combination of related rates problems, which are word problems you have to do all the setup, and graphing problems where you have to find the critical values. So it's kind of like writing a math problem from words where we have to find where something is maximized or minimized, and then we take the equation for that thing, take its derivative, set it equal to 0 to find where it might have a maximum or a minimum. That's where we're going next week. the last before 5.